So now let's talk about, let's get off resistors. Hell, I've blown an hour just on resistors. Capacitors. We talked about capacitors before. Here's our symbols. Units are farads. 1 farad is a lot. We can give some examples of that here in just a second. A capacitor, the capacitance in farads is epsilon times the area of the 2 plates divided by the distance between the plates. When I say plates, it's literally something like this. So you actually choose the smaller of the 2 plates, right? Because that's going to be the limiting factor. And you kind of ignore fringe effects. There's actually some stuff that goes here. But they're actually 2 isolated plates. If you look at the old days when they were first learning about this, Ben Franklin and whatnot, Leyden jars, it's a capacitor. It's a jar, it's a glass jar that's lined with foil, and it has a thing that comes, a probe that comes down the middle, and it's all isolated. And what you're doing is you're pulling electrons away from that metal, and that's creating an electrostatic field in between the 2. So there's fewer electrons on this side than there are on that side. It's creating an electric field, and that electric field is storing the energy. If you walk away from that, if you terminate that so that no charge can come in, a glass Leyden jar will hold charge for hundreds of years. Wow. A television tube, old style tube, those are giant frickin' capacitors, and they will hold charge enough to stop your heart for 15, 20 years. And the rule on those used to be that it was 1,000 volts per diagonal inch. So if you had a 36-inch television, you could count on there being somewhere around 36,000 volts on the back end of it at some amount of charge. So now you say, well, okay, well, what's that? I must have erased that one by accident. So epsilon is epsilon naught, which is the electrostatic constant, the electric constant, right? We looked that up just a minute ago. Farads per meter. Epsilon R is epsilon relative. In a vacuum, that's 1. It has to do with this. If you're in a vacuum, there's nothing to prevent an electron from jumping across, other than just the fact that there's nothing there. As you get different substances in there that can change, heavy insulators can make epsilon go up so that resistance goes up. But what really, where your biggest bang for the buck is either area of the plates or getting the plates really close together. An old style Mylar capacitor is literally 2 pieces of tin foil with a piece of Mylar in the middle of it and another Mylar on top, and they roll them up. The really old radio capacitors, they're actually brown paper. Yeah. And when you overcharge them and they explode, they blow confetti every freaking where. They go bang, and there's confetti falling out of the sky. And you're like, God.
I think we need to make some of those.
I have never I don't know if I've succeeded. I can't remember. All right, now the other, I did have it up here earlier. I erased it. So, capacitance is equal to QV, I think. Actually, that's little q. And current through an inductor, capacitor, C equals I dV dt. I equals C dV dt. I equals C dV dt. Is that right? Charge time voltage? No, it's the other way around. Voltage is equal to the capacitance times the charge. There we go. So, if I have, and let's see, a watt, 1 watt equals 1 joule per second, charges in joules. well, a joule is X number of electrons, so charge is the unit charge of an electron times how many there are, and you measure it in joules, and it's, I think Avogadro's number of electrons is 1 joule, if I remember right. There's a tie back there somewhere. So if I've seen some stuff that people have done, Ben Franklin and company and Faraday and all those guys did some stuff a billion years ago where they would lay down a sheet of foil and they'd lay down a piece of glass, and they'd lay down a sheet of foil, lay down a piece of glass, and they would take this piece of foil and wrap it over this one, and then they'd lay down a piece of glass, and they would take this other piece of foil that was sticking off from there and wrap it over this one. So they made a plate capacitor that was maybe, 10 or 12 sheets of glass thick and this big. And you can go through and measure the distance. Oh, glass is, 1/8 of an inch thick. So you come here and you say, this is a meter on a side, so that's 1, and the distance is 1/8 is what? 25.4 millimeters to an inch divided by 8. 3 millimeters. Yeah, 3 millimeters. 3 times 10 to the negative 3 meters. So already this is 1/3 is 0.3. So this is either 300 or 3,000. That moves up and becomes plus 3. But that's 0.3. So that's 300. And if epsilon, if you're using glass, that's a pretty low number, but already this number's big, and even though this number's small, even if that's still minus 12, that's 300, take 3 off of there, that becomes 24, it's 24 nanofarads. A decent sized capacitor on circuit boards in microfarads.
Yeah.
It's only, that's pretty big. And if you're charging it up to 500 volts, because you got so much spacing and it's a hunk of glass, it's not going to arc, you can stick a lot of voltage on that. And as soon as you say, oh, well, okay, this is 1 micro, 1 times 10 to the 6th, but I'm at 500 volts, you can -6. There we go. I'm sorry. Now you've got 500 times 10 to the 6th. 500 times 10 to the 6th is equals to 5 times 10 to the 8th Q. Electrons, I think. That's the number, and you can figure out, you can go back and look on yourself, is that joules, is that whatever, but that's a shit ton of electrons there. That's going to shock the shit out of you. Well, and you're at 500 volts, so remember we looked at the health stuff, how many, it takes what, 5 milliamps, 10 milliamps to stop your heart, and if you're 500 kiloohms end to end, that's only 5, that'll do it. That'll do it, and it's more than enough time to do it, because you've got so much there, your capacitance is so high. What happens is
The discharge rate.
you have, when you charge it up, it charges fast and then it slows off. It's an exponential. And then when you discharge it, it discharges fast and then it levels off. And this time here, I'm going to call tau. Well, I've done the math behind this. The point to where you get to like 98% charge is 5 tau, which is in seconds, and tau is equal to RC. So tau is your time constant, RC is your time constant. 5 tau, or 5 RC, is the time in seconds it takes to get to 98% charge if you've got a capacitor and a resistor in series and you've got a switch. Let's say I've got 2 switches. switch. There. So if I throw the switch to V, bang, I charge it. If I throw it to ground, it's a single, I can never remember, that's a single throw, double pole.
Single throw, double position. I think that's right.
Yeah, I always get those turned around. So if I've got 1 microfarad over there, 98% charge, yeah, you can work it backwards, but it's, you can come out with that and you can say this is basically how long, and this is not quite 5 tau, but it's pretty close. So you can say, well, it takes pretty quick to get to there, but so you can work these backwards, right? You can say, oh, well, I've got this much charge on the capacitor, and this is the resistance of my circuit, and this is how long it's going to take to discharge, and that sets you up a time constant. You can actually start working on filters and things like this.
Well, so on my NeoPixel strip, they want on the 5 volt supply. They recommend 1,000 microfarad cap across it to stop the spikes from damaging the NeoPixel strip.
Yeah. So what you're looking at is, so we come over here. Remember that. I have a piece of electronics. We talked about them being FETs, right? This is the standard transistor. Inside, let me do it this way. If you come into an inverter, the first thing you're going to hit is this. All right. Now, there's 2 things that happen. The gate of a field effect transistor is actually a capacitor. So whenever you have a signal come in, it comes in, it charges. When it charges, though, that's current moving through, right? Because I'm pulling electrons from this plate and moving them over to that plate. So that's current flowing. It stops DC. It's not trying to move it anymore. But an AC signal goes right straight through it because you're doing this. And bigger capacitance and lower capacitance, whatever, builds sort of its own time constant because of the internal resistance. So as this, let's call it 5 volts logic goes through, I get 5 volts here, and I get a 5 volt spike here, which is 0 to 5 volts, and this is 5 volts. So just a minute ago, this was probably at 0 volts here. Now I come here and I say C is, these are nanofarads and picofarads, so dV is 5 volts. If I'm running at 1 megahertz, that means that this from here to here is 1,000,000 times 1 times 10 to the 6th per second, which means this is 1 microsecond. And if I break these up into 10 pieces, so that, you know, they have a little bit of an edge to it, but it spends more time high than it spends low. So that means I'm going to have 6 tenths of a microsecond here, 0.6 microsecond here, 0.6 microseconds there, 0.1, 0.1, 0.1. Well, 0.1, 0.1. So 4 and 4, 8, 0.1, 0.1. So I say divided by 0.1 times 10 to the negative 6th, that's equal to 50 times 10 to the 6th amps, times C is a microfarad, so 1 times 10 to the negative 6th. Well, here it's probably picofarads, so millimicro, nano, pico, 12. So 50 times, so that's 50 times 10 to the negative 6 is 50 microamps. Would you say, well, that's not much? But when I look at my system and I've got a Pentium chip with 4 billion transistors on it, that just turned into 5 amps. right? P equals IV. 5 amps times 5 volts is 25 watts rolling off of that thing. Oh, but wait a minute, it's running not a megahertz, it's running a gigahertz. So add 1,000 to that, right? Loose, you know, I'm in the wrong order. I'm in the wrong order of magnitude here, but you get where I'm going. So now I've got 400 gabillion of these things that decide to switch at once, and this power rail that's up here that's trying to supply all of this has some resistance into it, even though before we said there's none, but we just explained how this copper trace has some resistance. Now I get all this resistance moving through this copper trace, gives off heat for one. The power supply, way the hell back here, remember we talked about going from the front of the breaker box to here, it can't supply enough. It's not, there's two ways of doing a power supply. There's source sensing and there's load sensing. So most power supplies look here at themselves and say, yep, I'm putting out 5 volts. Yep, I'm still putting out 5 volts. 5 volts. Your load out here on the other end is like, I only got 1 volt. Hey, I got 8 volts now. Oh, I've only got 1 volt. Hey, I've got 8 volts. And your power supply sitting here going, I got 5 volts. So then there's called load sensing, where they actually send a set wires out where the load is. And it's and your power supply's like, I got 5 volts. Oh my God, you've got 8. We got to turn this off. Oh my God, you've only got 1. We got to turn this on. And it tries to level load it out there. Well, you can't do that everywhere. You can't send. I can't send 1,000,000 wires all over my frickin' circuit board just to measure that, so that my power supply knows what the hell's going on. So what I do is I come in here really close to this chip that's got all these millions of transistors turning on and off and turning on and off, and here on the voltage line going in, V. And here's my VD. I put a big honking capacitor right there. Now, when everything's stable, he stores up all this charge on these plates, and he says, I need current now. Current is charge. It's electrons. He gives up a bunch of electrons right there with almost no resistance into that thing, and he says, here you go. And the power supplies, you know, feeding however much the power supply is, he's trying, you know, as you balance these things out together. And now he says, oh, I don't need anything. But he's like, oh, I'm just accepting this charge as it comes up. Yeah, but out here, if you look at this as a little bit of a resistance here, what you'll see is a fairly stable voltage here. What you'll see right here, you gotta look at it this way, kind of. If you look somewhere in here, you'll see the voltage doing this. But right here, you'll see it only doing a little bit of this. And here, you'll see it doing none of this. Right? Power supplies got this giant bucket of electrons that it's just pouring in. And these little, you can't make a change in voltage there because the electrons are right there when it needs it. Out here, this guy is making up the little differences. And so instead of being great big yanks back and forth, it's just little yanks back and forth. And you design your system to say, oh, well, you know, hey, if I'm going to be at this much current, if I'm running this signal in, it's going to give me this much current. I need this much current for this amount of time. So you work this all backwards and you come in and you say, this is how big my capacitor needs to be. There's a little bit more to it than that because you got the induct. If you look at any of these components, it's not a pure R, it's not a pure C. If I look at a capacitor, I've got this, but then these wires have a little bit of resistance, and they also have a little bit of inductance. So you get a model that looks like that. And your resistor, the wires, there's a little bit of capacitance across here like this, and the wires have some inductance like that. And it's really a very complex circuit, and it has a sweet spot where they'll have a Q. Where Q is maximized or minimized, there's like a peak there. And so at that frequency it's resonant and it likes to do something different. Which could be, it could Q down and say it blocks signals at that particular frequency, or it could actually have a tendency to amplify signals at that particular frequency. Which is how an oscillator works. part of. But at that resonant frequency, fun things start to happen. And to do the design actually correctly, you got to look at those are called bypass capacitors. To do the bypass capacitors correctly on your circuit board, people just usually throw in you'll often see a 10 microfarad, a 1 microfarad, and a 0.1 microfarad. Because that worked in 1 megahertz and 5 megahertz circuits back in the early 80s on PC boards, and people just sprinkle them all over the place. And they could actually be, rule of thumb, I'm going to use these. They could be actually making the problems worse. Because you've got this track resistance and you've got this track coming in that has some inductance, which we'll talk about here in a minute, and you're making a resonant circuit. So to do it right, you need to go in and you need to take a look at what your topology is. And you want to, capacitors need to be as close to that pin as you can possibly get them. But you want to say, oh, well, I know I'm using a plane like this, so there's this parasitic capacitance, these parasitic inductances, and you want to be smart about how you choose them, because there's different styles of capacitors that have their own properties. So you want to use like a 10 microfarad tantalum, but you'll want to use a 0.1 microfarad ceramic, and you'll want to use a 1 microfarad mylar or something like that. So they each have their own, their curves, their characteristic curves are different. And you want to play the game. Just throwing a big ass capacitor there is not always enough. It can actually do the wrong thing and hurt you. The other thing that happens when you do this, if I've got some other device here that's soaking current left and right, I've got two wires next to each other. Length is really long, width is really thin. D's kind of wide, but it's still two wires. Two wires is still two plates. There's some area there. And so when something starts wiggling on this wire, when you start throwing a square wave down this wire, some of it's going to it's called a crosstalk onto this one, and it's going to induce a signal over here. It's called capacitive coupling, as opposed to inductive. There's also some inductive coupling there too, but in this particular case, capacitive coupling. And so when you're down at a circuit board level, you've got to be careful with your layout. You want high-speed signals. You want to put ground planes around them so that it protects them, and so that their noise doesn't leak out onto other things and do other stuff. So that's one of the practical uses, is to keep your power supply clean at the point that needs it. Another practical use is a filter. So we talked about the noise equation, Boltzmann 4KTBR, and we talked about, I said remember this, 5 tau. I can this is a low-pass filter. I'm sorry. Do it this way. This is a low-pass filter. This is a, I'm sorry, got it backwards. This is a high-pass filter. This is a low-pass filter. If I look at this in the frequency domain, I'm going to see here, remember we talked about how low frequencies this blocks a low frequency, very slow change. The change is so slow when you look at that I equals C dV dt. When you look at that, the dV dt is practically zero. It's moving really slow, so current's zero. There's a little bit there, but not much. But on the other hand, if I'm moving really fast, like we showed here, current goes really high, right? So if I look at this, what happens here? A high frequency, I should do this. They're both true, but this is a little easier to see it conceptually. So here, a high frequency goes straight to ground, right? If I put 1,000,000 megahertz on that, it's going to go here, and because that lets high frequencies go through. Because C dV dt, dV dt is practically infinity. Because dt is so small, you know, if this is microseconds, that becomes millions. If it's picoseconds, that becomes billions. And so current shoots through the roof up to whatever the capacitance, this capacitance is. So wham! Everything that you can possibly source goes this way. And so nothing makes it past here. So if I look at this as frequency, and I will make this one orange, you'll see that it looks like this. Let me extend this out. Lowercase f for frequency, capital F is farads. And this point right here is RC. Two pi RC. 2 pi RC. And this is the point. This, if you were to extend this to a line and bring a line up this way, that right there is 3 dB down. Half power. So that is your pole. So you start talking about a 1-pole filter, 2-pole filter, 3-pole filter. This is a 1-pole filter. And at F sub C, you're 3 dB down. Half your power is lost at F sub C. If it's a 2-pole filter, well, that's just, if you want to stay stupid, well, if you want to stay not clever, let's put it that way. R, R, C, C. Now a 2-pole filter will move this in to here. A 3-pole filter will move this in to here, and so forth. It'll move your frequency to the left. And this here is for an RC filter is at 10 dB per decade. I think it's 10. It might be 20 dB per decade, but I think it's 10. But if you go to a 2-pole, then it gets sharper, it becomes 20, and if you go 3-pole, then it becomes 30. And this gets sharper and sharper and sharper.
The more poles, the sharper the...
Yeah,
okay.
but what you see, well actually, so F sub C still stays here. What you see is a thing that goes like that, and then to get there, it starts a little bit earlier, but that 3 dB point stays in the same spot. It just gets sharper and sharper. But to do anything realistic with this, it takes so damn many R's and C's that it's not worth the effort. You want to get into active components and use active filters that amplify the effects. The flip side of this is red. Think about this. What happens here? Low frequency stops. It doesn't go through, right? Because the capacitor blocks it. So it just kind of goes to ground through the resistor. High frequency, on the other hand, zips right through. So now we're talking power out here in this domain. You can have all the voltage you want, but there's no current going through. So the power is 0. And you can have all the current you want, but if there's no voltage, it's still power 0 being delivered. So you can talk about balance of power, but what happens here is now if I have 2 pi RC here, this guy turns on and does that. So that's a high pass filter and a low pass filter. And now we're going to do a level of abstraction here. And I'm going to say if I put a high pass filter in series with a low pass filter, I get this curve, right, which is a band reject filter. And if I put a high pass filter in parallel, let's see, let's use a different color. What I got here, green. If I put
So essentially, the bandpass is basically giving me a very close, narrow scope to chop out.
yeah,
Yeah.
it's a notch. It's also called a notch filter.
I think in terms of audio, a bandpass filter is like remove this frequency.
The best way to think
not
about
like
it's
huge.
It's a notch filter, and I like to talk about it as tuning in the dad notch. Talking to your kids and they tune it right in and they can't hear a damn thing you say until you say the word money or something like that, and then it goes away and they're like, what?
Yeah, I had a question about audio. So that amp that we were talking about before, the guitar amp, so it was apparently a bad filter cap, which is why it had a really bad hum.
Yeah.
And then he replaced it, but the schematic was wrong, so we had one on us back and eventually got it fixed. But so which filter is that, or how does it apply in the theory and the practical?
Okay, so in that particular, okay, back up here for a second. If you put a high pass in parallel with a low pass, then you get the inverse of this. Is that right? High pass blocks. Yeah, because the high pass, maybe I have it backwards. One's a band rejects and one's a band pass. So one notches it out, one lets it through. And I'll let you do the math. I probably got it backwards there. But anyway. So now, what you're asking about, power supply design. We talked about before, you take your power off the wall as a 60 cycle, 60 hertz. That hum is 60 hertz. About there, right? Give or take. What you do is you go through, on a really old system, it'd be a half-wave rectifier, and you get this. If it's a full-wave rectifier, you get this. So actually, you're probably hearing 120 hertz. And so you do this game right here. You have a filter capacitor, and you kind of know what the resistance of your power supply and everything else is. So you choose this capacitor here, based on the load that you're going to see out here, so that what happens is, and this is exactly what happens when we showed it up here close, only we're talking higher power now, you basically get this. It fills in these gaps between the peaks of the sine waves. And so this is called your ripple current. And if you get that down suitably low, you won't hear it. What you're looking at is, do I have to draw tubes? Tube. Cathode, heater. Let's see, cathode's tied to ground, heater's usually tied to 5 volts. A tetrode would be, or a triode would be, here is your gate, here is your plate, and this is 200 volts-ish, 250 volts. And this is all in a piece of glass that's been evacuated. And so as you heat the cathode with this cathode heater, it's made out of tungsten, and electrons boil off. And this 250 volt positive plate draws the electrons across, and then they'll put a big honking resistor here. And as the signal goes in here, your audio sine wave goes in here. As it goes positive, it accelerates them through, and as it goes, or lets the electrons go through, and as it goes negative, it repels the electrons. So what you see here in your current, as this goes positive, the current goes with this, and this voltage here goes with this. So you notice they're in phase also. And on a tube, you get what's called a grid leak. Some of the current goes out the grid. Then they came up with tetrode, well, there's a quattrode, where they added another one here that goes to a bias. and then they became a tetrode. Tetrode? I think it's a tetrode, where there's another bias here, and those help stop grid leakage and give better control and do fun stuff. Practically speaking, though, this is up here on your power, and your power is doing this. So it's pretty level. And so, you know, if that's, you know, only a volt out of 200, you know, if that's 2.5 volts, if that's a 1% ripple, 2.5 volts out of 250 isn't very much. And so there's not any real big effect here. But if this thing is, if that capacitor's blown, now this too, you know, I'm sitting here putting, let's say I'm putting a 1 kilohertz tone out, right? So if this is a kilohertz, 4, 5, 6, 7, 8, 9, 10, and that's 120 hertz, that's doing that. So my tube's coming alive and it's dying, it's coming alive and it's dying. And I hear my sound, even if there's no sound at all, if I've grounded out the microphone input or the audio input, this thing's going to hum at 120 hertz. And as I start putting audio into it, it's going to, you're going to hear the audio, but you're going to hear this god-awful loud tone on top of it. That's what you had. That's one of those things, as soon as you hear that, it's like, yeah, oh yeah, it's over here in the power supply somewhere. And usually what happens, I'll use what's called an electrolytic cap. So electrolytic capacitor, it's not air in there, it's not mylar, it's a an electrolyte that's liquid, and after time they dry out. That's what happens. Or sometimes the capacitors, they get old, if they're the old paper wrapped kind, they'll like get little holes and they get little arcs in there and it just quits working. So yeah, so I could replace this whole block here. I could replace this whole block here with 5 volts or maybe 15 volts and a single BJT like that. That's got a lot of the same effect. A well-designed transistor amplifier is just as good, if not better, than a tube amplifier. The difference is on a good transistor amplifier and an equally good. It is much easier to build a transistor amplifier of better quality. A transistor amplifier will almost nearly always have better phase noise, better harmonic distortion, and total harmonic distortion. The problem is that when you overdrive them and put in too loud of an input signal, which everybody does, on a transistor circuit, if I put in a sine wave, I start getting it chops it. So I get this thing that looks like this.
So you're losing frequency response, correct?
It's a odd harmonic.
Okay.
Because you're starting to approximate a square wave. Whereas on a tube, when you get onto them, they compress, and instead of just chopping off, they get this more of a, they kind of, let's exaggerate it.
I think I got it.
You start getting a thing that looks like this, because you're hitting in the overhead. Whereas on a transistor, it just does this.
So is it like the clipping of the audio like on a telephone?
Mm-hmm. So the truth is, the transistor amplifier is better as long as you use it inside the realm that it's intended to be used. As soon as you go off and you start overdriving the thing, the transistor amplifier just cuts it off, and oh God, it's this grating sound, right? That's this third harmonic that just hurts your ears. But the tube amplifiers, they lose linearity, but they don't just cut. So it gives them a sweeter, a warmer sound. If you're using them right, transistor one's always better. Always. When you're not using it right, tubes sound better. And it's become a thing. People were so used to, because people always overdrive their shit. Look how loud I can go, and look how good it still sounds, right? Now you take people, if you take people who have listened to tubes and they've trained themselves, if you put it behind a wall and you put the exact same speakers and you don't overdrive them, which one sounds better, they'll always choose the transistor one. But if they know which one it is, if it's not a blind test, they'll always choose the tube amplifier.
I'm going to take you to a bar with some audio files and watch the
Oh, this will cause people to be pissed off and argue and scream, but I've seen the test done.
My wife's dad, he's like an audiophile nut, but he's like 75 years old now, and he claims he can hear the frequency difference between this stuff, and I'm like, dude, no way.
Well, no,
first of all, you can't. I think like he's talking actually not tubes so much, but CD versus that, which I mean is essentially the same thing in the sense that there's not. I think though it's not about frequency response. I think it's about that warmth that they're used to, which are those tones that are in there, no matter how good your needle is, that people like.
Well, a record does sound nice, but again, so here's where you get into, I'm talking about Class A amplifiers. Every tube amplifier, for all intents and purposes, is a Class A. And we talked about that at one point where, gee, I can do a Class A and my signal looks like this, but damn, that uses a lot of power, because when I come back here and I look at the transistors that are driving this thing, they're always on. There's always current going this way to ground and being wasted and using lots of power to get very little output. And holy cow, that costs a lot, right? I can get almost exactly the same response if I go to a Class B amplifier. And a Class B, I bias these a little bit. So right in here, in this little voltage range, which is about 0.6 to 1.4 volts, depending on the kind of stuff I'm using, I can turn it off. And now in this area where they're both on a little bit, they're both off, and no current flows. Now, but what I get is, so this is Class A. I get Class B, which looks like this. Now you get this discontinuity right there. And that, I can't hear it, but people with good ears can hear it.
Yeah.
And so that's Class B. And then they came up with orange. They did something that's sort of in between. It's called a Class AB. So you kind of do a number that's in between, and then it kind of cuts over at an angle like that. And it's softer on the ears, but it still saves power. And then you can go, what's a Class C amp? I think an A is always a push-pull. The way this sort of works is you do, your speaker out here has two wires in, and you're doing a push-pull. Oh God, it's been a long time since I've done
Class
these.
C is less than 1/2 cycle of the input signal.
Is that what it is?
That's what it says here.
All right. All right. So Class C then, if that's what it is. So Class C, I do this half and only this half. So it's still going to vary in amplitude to give me loudness and not loudness, whatever the opposite of loudness is. And it's going to vary in frequency.
We're going to say really crappy?
Actually, it's
not as...
That's a Class C amp,
Okay.
probably.
Yeah.
It's got some tinniness to it, but if it's a reasonably well-designed circuit, yeah, you can hear it, but it's not horrible. And it's good enough for a freaking CD. And then you can go to Class D amplifiers, which is what you're starting to see now, where what they're doing is purple, blue, orange,
And is the
green.
whole reason just for power efficiency?
Power efficiency. And these things are going to Class Ds.
In order to. Yeah.
And what a Class D is, remember we talked about pulse width modulation? And playing back audio with, that's what a Class D is. Now you're varying a square wave based on the frequency. And the actually based on the amplitude. You put out a 100 kilohertz square wave, and here it'll go fast, and here it will go, you know, just barely on, and then here it'll be on like the whole time, and then here it'll be barely on, and so on and so forth. And so you do a you know, I should do that. Send me a text or an email. I'll do like a microphone in to a PWM out. I'll just do a direct conversion, and we'll hook it up on an Arduino, and I'll talk into it and hear your voice come out the other side. And because I won't remember that, but that's you know, 50 lines of code or something. It's not awful. So that's a class green. It's Class D amplifier, I believe. So we've bounced to capacitors. We've gone to practical use 1, which is filtering your power supplies. Practical use 2, combined with a resistor, is a low pass, a high pass, a band pass, or a band reject. The last one I'm going to give you is an Electret microphone. So the microphones you buy now, there's two kinds of microphones. There's a piezo, and there's three. There's the carbon resistive. There's a piezo, and there's an Electret. Electret.
Electret.
Electret. E-L-E-C-T-R-E-T. Electret. The way it works is this. I have my voice coil, or I have my voice cone, right? And I'm talking, and it moves back and forth as sound waves impinge on it. And on the back side of this thing, here is a metal plate. Bring it this way. And here is a squishy polymer. And what they do is they charge this. So that's loaded, so it's got extra electrons in it or something like that, right? So if this thing's just sitting idle and it's not doing anything, there's electrons in here, which means there's an electrostatic field in here. Yeah? With me? Now when I talk and a sound wave hits this, it squishes it closer together. V equals QC. Q is constant because those electrons are loaded in there as graphite particles or whatever else, so it's not going to change. But my plate dimension changed. Plates got closer together, that went down, that means voltage went up. And now as they move apart, voltage goes back down. And the Electret microphone has 3 inputs. Have 3 inputs? Yeah, it has a FET in here, a JFET usually. So here's your 3 inputs. Just 2, what's a third? You've got power. Oh, it has 2. Some of them have the third built in. So there's a resistor in here, and that's might be the third output, depending. Some are only 2, and you have to put this resistor in yourself and take your own output. But you basically tie this to ground, so this is your ground, and this is VCC, this is your power to it. And now what you're doing is you've got your power rail out here that you're powering everything else off of, and it comes in and hits this Electret mic and goes to ground. So the way you pull your signal is you put a resistor here and you pull your signal right there. And you want to have a good capacitor here, otherwise you're injecting whatever's on this back into your power supply. If you got a really stiff power supply, that doesn't matter, but if it's just a half-assed power supply, that can be a problem. Electret microphone. They generally, if you put 5 volts on them, this voltage right here, if I remember right, is about 1.2 to 1.5 volts. And you'll never see a signal bigger than about a volt off of it. And it has absolutely no current. So you have to have a high impedance amplifier on the other end to convert that.
What kind of mic are the old ribbon ones? Do they fit in any of these?
The old ribbon ones. Those are the ones that had like the membrane in the front of them.
Right.
I think those were a piezo. So a piezo, and it's not what we're going to talk about tonight, but we'll talk about it for a minute. A piezoelectric material changes shape with a voltage put across it. So it's a stressed lattice crystal, and as you cause that lattice to bend, it creates a charge differential across it. And by the same point, so you can measure the voltage off of it, but you can also turn that around and use it as a speaker, because as you put voltage on it, it causes it to flex. So a piezoelectric material can be an amplifier, or I'm sorry, it can be a speaker, or it can be a microphone pickup, depending on how it's made and what they use it for and whatever else. So I think after almost 2 hours, we've beaten capacitors to death.